it's going to be important that we leave the planet and be able to live in other bodies. Initially, in our own solar system, there are kind of three scientific questions. Where did we come from? How did we get here? And are we alone? The memory in your cell phone is far in excess of all the memory that was on the Apollo satellites collectively added up.
So I know a lot of people complain about how expensive space travel and spaceflight is. So if you were a spokesperson for NASA and had to sell these people on the space dream, what would you tell them?
Well, that's the same question, if you think about it, that Columbus faced, Juan Pizarro, Shackleton, any explorer who was setting out into the unknown and needed a lot of money to do it. In the case of NASA, and I think the spaceflight program of many countries, the one objective is it's important to us, and in my opinion, anyway, at least the community, to understand increase our knowledge of the universe, humanity, how we got here, where we're going, and are we alone? I mean, that is an underlying thirst for knowledge and curiosity, and that's fundamental. Explorers, that would drive many of them. The second thing that drives them is looking for expanded resources. In the case of many early explorers, they were looking for gold, spices, and things to bring back economies or into, agricultural and things that they could do in newfound countries to expand their food supply, their return. In our case, I believe that it's a kind of important. Number one, there are valuable resources out there that can be returned to Earth for use, but more importantly, I think for sustainment in the long term, a million years from now, 10,000 years from now, it's not clear when we'll need it. It's going to be important that we leave the planet and be able to live in other bodies, initially in our own solar system, because we're going to use up at some point all the resources we have on Earth, or unfortunately, conflicts, as you see on the planet, could end up with destroying the human race, and the ability to get it and sustain it in another spot in the universe is important. And then finally, I think the third point I would argue is that it engages the imagination of a lot of young people to pursue science and engineering. And they don't really have to go into the space program, but they will make a difference in the quality of life, the biomedical devices we have, our ability to detect and cure diseases. The communications increases communication, such as the communication satellite industry allowed us to communicate around the world globally instantly. I'm talking to you and you're in South Africa at this point, and I'm sitting here in the United States on the East Coast, and we're talking as if we're in the same room. And finally, countries look for technology leadership and pride. And the Cold War was going on when the United States really put a lot of resources, money, people, and our technical talent into it, and that was an important thing that drove it. But each country would like to think that they have technology to be competitive with the rest of the world, that their education system, their workforce is as talented as the rest of the world, and space has given one venue to demonstrate that, and gives a lot of pride.
Do you believe that space travel, space exploration could be, a beacon of hope for humanity? Because as you mentioned about the rising conflicts happening in the world, I mean, you see with what's happening in Ukraine, with the Russia invasion, and you also see things like climate change and rising sea levels. Do you think space exploration is going to be tied to the future of humanity?
I believe it's going to be important to have that capability, and it's going to take a long time for us to build up the capability to actually go to Mars, or and sustain ourselves there, and sustain with the medical, the food, the environmental conditions, all of the things we might need to build habitats and the food and water supply and all the other resources we need to survive. And so I think the investment delay will give us that opportunity. Hopefully, at the same time, we'll also find ways to control of the environment, our own planet, global warming, and also I would like to dream, but like everybody else, that one day we'll find a way to work together um, as a planet, all civilizations, all different countries, races work together as a single entity. And um, I think, though, as a backup, staying let me just say, it's to sustain the human race. Um, Exploration is an important option, and developing the capability to live on another body is important.
I've noticed there's a couple of countries that are placed on the ISS, but I've just always been so curious as what happens. Does each country's territory on the International Space Station, is it off limits for the other countries? Do they do their own research? I mean, what happens on the International Space Station?
Well, let me start. Number one, it's a large um, space vehicle that's made up of many components that are required to work together. For example, the big solar arrays are provided by the United States. A lot of the early communications and power management resources and propulsion were provided by the Russians. Today, these still have to work together. You take one away and you don't have it. So we continue to work together as a partnership to sustain the infrastructure. The Japanese have added a module. Um, the Europeans provide a lot of reboost capability over time, have provided reboost capability. Any one of these, without it, would be a shortfall in the capability we need to sustain it. So, regardless of what happens on the ground in politics, we have continued to work together with countries that currently there are some adversarial relationships like Russia. We've continued to work together in space to ensure that the space station is maintained. In terms of science, every many countries have contributed, have performed science experiments, both their government researchers as well as their industry, their pharmaceutical companies, their materials companies have performed experiments on the space station. These are performed on whatever research facility on board would support the research. And at any given time, that could be from Russia, from Japan, from the European Space Agency, from Canada, uh, and so it's sort of at that level um, countryless or nationalityless. It's basically a scientific endeavor. It proposes research. It looks at the resources on board and uses the one appropriate for the research. And the experiments are actually carried out by astronauts from different countries. I mean, the Russians, the Italians, the Japanese, the Canadians, as well as the Americans, all have astronauts up there. Every time there's a six-man crew, that a six-person crew, not man, but six-person crew that's on board and made up of members from each of the partnerships. And at any time, one of them will be one or more of them will be performing scientific experiments for people who've submitted the experiments or sent up the package to be tested. Um, from the ground, and again, it's without regard to nationality.
What's the future of the ISS? Are they planning to have a base there where, let's say, before we go on other missions, are astronauts going to, stop there, or what's the future of the ISS?
Well, if you think about it, it's not too different than some of the early endeavors in the aircraft world. And when aircraft was built and particularly focused on performing government services. Early delivery of mail in the United States was an industry, a government procurement of service from industry that helped grow the airline industry and sustain it and let it build the infrastructure needed to safely carry and transport passengers, and airports were built, and things were spawned by what initially started. So space station is a little like that. The governments have been the primary funders of it to build it, put in place the infrastructure. To sustain it is not an inexpensive operation. It is sustainment on an annual basis is in the multi-billion dollar range, and it's support provided by all of the member countries, as well as some subsidized by commercial entities that pay for government services on board to carry out their research and experiments. As we go forward, the United States and now the partners, I think, have all come to a sort of a consensus that after 2030, um, we really need to look to commercial and private industry to start putting in place and taking over the infrastructure. The current path right now is there are several initiatives in the United States and other countries, China for that matter, in a different form, to put in place space stations that will ultimately replace um, the International Space Station, probably with newer technology and easier to maintain at the same time, or less costly to maintain and maybe easier in terms of logistics. And many more countries and opportunities are there to get um, astronauts who are non-government people or up to the space station, and we're seeing that with SpaceX. That'll ultimately evolve with a number of other providers, Boeing in the not too distant future. So all of this is leaning towards commercial space station infrastructure with new technology, a new commercial space station, and phasing out of the International Space Station. And current predictions and current estimates and funding says that's the transition from government-owned space station to a commercially owned and operated space station as a primary resource would be around 2030.
I wanted to touch on you a little bit. I've been super curious as to what led up to you doing what you do. I mean, before NASA, before the science, the human space programs, what was it like growing up for you? How was your childhood like?
Well, I was always from probably the third or fourth grade, and that had to be 8 or 9 years old, was always interested in building things. On a walking home from school in the second and third grade, I would stop by a construction site and grab some surplus wood. In fact, it got to the point where the construction workers would have a little package for me to bring home. And I'd be hammering them and putting them together. So I always like to build things. My first fishing rod, I didn't want to buy one, I built one. You know, and it didn't work real well. I didn't catch a lot of fish, but I learned a lot. So I apparently I look back, had a curiosity and a bent towards building things. I later on I began to look up and wonder what was out there. In high school and elementary school rather, I also performed a lot of belonged to the science club and uh, built a lot of little science experiments that I enjoyed doing. And unfortunately, as I got into my teenage years, I kind of got bored with school and lost interest and ended up not going to college right out of high school, but joining the Navy. I wanted to kind of explore and see the world. And in the Navy, I ended up going to a school, a technical school, to learn how to maintain a complex aircraft uh, bombing system for high altitude bombing that had all stabilization, power, all of the elements of a spacecraft or anything as part of the system. And I developed a strong curiosity. How did somebody ever design this and put it together? And that stimulated me, along with encouragement from the pilots that I flew with from time to time, to go to college when I got out of the Navy. And when I did, I didn't have a lot of money, so I went a couple of years at night to a local community college and got what's called an associate degree, a 2 year degree, and was hired into to Grumman. In the meantime, I also got married during that, and still married 60 years later to the same wife. But so I right out of college, I had to go right to work, and I did. And when I was in Grumman, after about 3 months, my immediate supervisor um, decided that he needed to supply an expert in electronics to a space program and tapped me for it. I had at that point had a strong interest in space. I watched the communication satellites being launched. I got to try to see the John Glenn early spaceflight launches when I was stationed in Florida in the military. So I had what's how's all this work? And I love to see the technology and things remotely operated. And so when I got taken over and joined this space project 3 months out of college, and meanwhile I was back in school, going for my bachelor's and master's at night and working days full time, um, I got into my dream job and never looked back. It just got me in. It turned out everything came together. My curiosity was kind of started to be satisfied by learning on how systems were put together with my initial college and following through and I never looked back once I got on the space program. I loved every minute of it. I was one of these who was up early in the morning, in early, left late, went to school, went home, and repeat the next day, and did that, and found time to work with my family in between, and enjoy my life with my family in between. And as I recall, all my three of my children ultimately came from my college graduation from my bachelor's degree. The whole family went. So that's sort of how I got into the business. It started with an early curiosity, and fortunately, things fell into place. Not exactly planned, but fell into place. I prepared myself. There were opportunities, and preparation and opportunities came together.
What does it take to work in an organization like NASA? Because I'm sure a lot of people would be curious to find out.
Well, I had three phases sort of in my career. I started out with Grumman Aerospace and worked there for 17 years. Then I joined NASA for about 18 years, and then the last phase of my career has been in commercial new space startups. And NASA was an exciting place to work. It was when I worked at Grumman, it was my dream to be able to actually work at NASA. And why? Because I knew for while I was at NASA, I was going to do what I love to do. At Grumman, unfortunately, it's a company with contracts, and if you lose your space contracts or finish the job and there's not a new one, you get on an aircraft program or some other program, which to me was not as motivating as and exciting as the space program. So I was fortunate when I finished up a project that an opportunity to join NASA occurred. I did, and it was I went from in 11 years at NASA, went from operations project manager developing the operations to Hubble to center director at Goddard, and then finished up my career as head of human spaceflight. So I got exposed to, from my perspective, um, all aspects of spaceflight, operations, development, uh, space science, earth science, and ultimately human spaceflight. So it was an exciting experience and worked with a lot of good people. And that of course, was what really made what I did and the missions I was on successful is the amazing people at NASA that I got the chance to work with and learn from and never stopped learning until even when I retired, until I retired.
Yeah, and I wanted to ask, what was your first mission like? How was the room? How were the stress levels? I mean, just how was that entire process like for you? Being there for the first time. Yeah, how did it feel like?
Well, my first mission was when I was in industry. It was Grumman. It was a program called the Orbiting Astronomical Observatory. It was the first, and the first flight was one of the first of four missions. And the first part of it is just um, it was in an era where Apollo was being also built at Grumman, or pieces of it, the Lunar Excursion Module. The space industry was thriving. It was the darling kind of um, engineering positions to have of the darling. What I meant is the kind that everybody desired to work in the space industry. And it had plenty of money. When President Kennedy committed to land the man on the moon by 1969, the person on the moon, he basically also had the support of Congress and the industry, and everything was focused on it. If you went on an airplane with a package and said, we need to get this to the Cape for a launch, the airline went out of their way. Everybody supported it. It was kind of a national goal that everybody recognized. So that was the first part. So that was an exciting time. I got involved in this smaller program and went to the Cape and started to set up for the launch operations for it down there. And I got to see a launch every week. Some of them were exciting, and some of them were even more exciting. They didn't make it. It was in the days when one out of three or so didn't make it to orbit for some reason. I also got to see some of the early Gemini launches with people on board, and they were particularly kind of thrilling and excitement, and also at the same time there was a lot of trepidation that there were humans on board, and you didn't want to see it blow up like the last unmanned or robotic spacecraft you saw mission you saw launched. And fortunately, in my days there at in my early days of my career, all those launches were successful, and human spaceflight program didn't suffer any early human loss. Later on, it did, of course, several times, three different major occasions. But anyway, so backing up, so that was the first part. Then the second was actually getting involved in the launch of this first satellite, and I had the good fortune of being in the what's called the blockhouse right underneath the launch pad, because I had one of the things my jobs were is to support controlling, um, making the final measurements, and also providing power to the satellite while it was sitting on the launch vehicle during the countdown, and then committing that it was ready to launch. I was part of a two-man team that sat in the blockhouse, and we would get inputs from our team who was monitoring the satellite back in the control center, the launch control center at the Cape, and also back at Goddard and Greenbelt, and they would be looking at data, and we would be making sure the power was there and the data was getting to them, and they would report to us, and we would to commit the countdown. And as a 24-year-old right out of school, I was just amazing. Okay, and we only had two words to say during the countdown, and that was um, oil ready, and it was almost comical because we knew that was going to be on the radio, not television those days, maybe, but it's on the radio, and so we practiced, we rehearsed those two words. Oil go, we did very things trying to sound very, and then when the time came, of course, we performed. So that was the good part. The bad part is the first spacecraft we launched failed 3 days after launch. Many things went wrong for it. The plus side of that is we learned a lot. It was the early phases. Most of the things were things we couldn't have tested on the ground, or when we did test them, we didn't really understand what was happening and how it translated to what might happen in space. And we assumed that everything was going to be working as it should be. And of course, in hindsight, we found out there were a lot of signs in the testing on the ground that we would have problems in orbit. The second piece was the orbital environment was slightly different in certain areas than anybody expected. And that caused, in fact, that was the underlying cause of the primary failure, is that there's an atomic oxygen rather, atoms rather, that are still coming off of the materials from Earth. It's outgassing, no different than the film you get in the window of your car over time if it sits in the sun from the plastics inside. But that outgassing also released um, atoms and molecules, and these unfortunately conduct electricity. And when we turned on the high voltage, there was still outgassing going on, and the high voltage shorted out and um, damaged a number of the systems on board, and which became fatal to the satellite. But we learned that, and the whole industry learned it. And so, but it was a disappointment personally, but and to all of us who worked so hard on this and worked night and day for a few years to get it, 2 to 3 years to get it up there on orbit, and people. But on the other hand, we learned a lot, and the second one was very successful, and there were four in the program. The third one, unfortunately, the launch vehicle failed. Another lesson, you can't always count on success, although we knew that from history, but again, a major disappointment. And then the fourth one was a success. So my early career, it fundamentally set the stage for me in the future, because I learned that whenever I see anything on the ground and ground testing, um, we try to really we do everything we can to find what we call the root cause and understand it. And that kind of analogy or that kind of technique, because if you don't, you're going to find it on orbit, and it's going to surprise you, and you're going to, potentially lose the mission, and which we did. So that gave me a certain discipline built in, and anybody I ever worked with or trained with or trained to work for me, I always instilled that in. The space shuttle culture was that later on. Clearly, I didn't set that culture for space shuttle. They had that culture ingrained into them, especially after Challenger. But on the other hand, I reinforced it when I was associate administrator. But it sort of set those early failures, set the stage for my whole career and what kind of discipline was needed for success and successful space missions. Post NASA, I was able to instill that in some of the people I worked with and mentored in my experience in new space.
When you watch NASA missions on TV or on YouTube or anywhere else, it doesn't show how complex or precise every mission actually is. So I'd love to hear your perspective on the background and the behind the scenes of what goes into a mission.
Well, there's a number of phases, that are important, and you can't disconnect them because if you do proper early planning, understanding what you're trying to achieve, what measurement you're trying to make. Are you trying to measure something on Earth? Are you trying to measure wave height, water resources, the atmosphere? You're trying to measure something about a planet or see, take images of look at stars. Um, all of those drive, and what kind of risk do you want to take? In other words, you can spend a lot of money and make the system bulletproof, but it takes a very lot of money. JWST was a $10 billion program and a very long time. JWST started, and we started at Goddard when I was Senate Director in 1995, and it didn't get launched until 2000, 2001. Um, December 2001, Christmas 2001. So a long time. Or do you want to spend a lot less money, take a lot less time, but take a little bit more risk? So those decisions are made early in what kind of satellite do I need? How much do I want to ask the Congress in the United States, ask the government for, and how much do I want to commit to? The second thing is that particular mission, whether it's Earth looking, star looking, communication satellite, you then have to decide what orbit it needs to be in to perform that mission. What is the approximate weight and size of the satellite? Therefore, what kind of launch vehicle do I need? What time? So, able to do all of the study work upfront to define all these parameters is very important because that not guarantees, but prevents as you're going forward surprises. Oh, the satellite suddenly weighs twice as much as I expected, and I only planned for this launch vehicle. And by the way, it doesn't fit physically on another. All of that needs to be done. So there's a lot of detail that goes into that, and then that goes into system design and power and thermal and a very complex engineering problem. Not to mention the fact that whatever instrument I'm using may or may not have technology that currently exists to carry out the measurements. In fact, some of the most important missions drive the technology development needed to carry out the mission because they want to advance the state of knowledge or the state of the art. And again, that all has to happen long before launch. And then once you do that, you have to put all the pieces together, make sure they work, lay out how you're going to operate it, and then do launch rehearsals, operations rehearsals, training of the staff. Um, Meanwhile, you have to build and deliver the satellite to the launch site. Meanwhile, the launch vehicle is looking at the satellite. Now the launch vehicle engineering team is looking at the satellite analysis and they're saying, okay, when I put the two together, now I'm going to launch at a lot of vibration. How are they going to play together? Is the satellite going to come apart or will it survive it? And and um, and so they do an analysis and make sure that the testing on the satellite and the design, for that matter, is going to withstand the launch environment. So that process goes as you start to bring the pieces together, the launch vehicle, the satellite together. Then finally, you go through a whole environmental test regime on the satellite. You subject it to the vibration test that's going to experience at launch. You sometimes have to build an engineering model and test it first and really test it and understand the full level it's qualified to make sure there's enough safety margins in there in case the vibration is a little more than expected or it gets hotter than expected. Sometimes you're confident enough in your ability to analyze the environment and the satellite design that you don't need engineering models, and you proceed right into environmental testing on the flight unit when you build it. And again, it's vibration, thermal vacuum, electromagnetic compatibility. That is, the systems can talk to each other without interfering with each other, and you can get the proper data signal and communicate to the ground and get the commands in. You have to demonstrate all of that on the ground, and then you have to demonstrate you can execute a typical orbital timeline. Turn on the instruments, turn them off. They don't get too hot, they don't get too cold. All the data can be moved to the ground. So all aspects of it. And then you get ready to launch. So you move it to the launch site and you verify that nothing happened in transit. You do everything you can to protect it. Some are flown to the launch site, others go in containers over the road, but you make sure that it survived that, it's ready to launch. Then you made it to the launch vehicle. And again, you're watching through all of this the parameters that temperature, voltages, uh, information, data rates, communication, link strengths. Are we still getting the same power out of the satellite? Making sure nothing changed along the way. And if it does, you have to spend a fair amount of time understanding why. Because if you don't, again, you'll be surprised on orbit one, and that's a surprise nobody likes in the space business. In fact, nobody likes surprises, but in the space business, other than new discoveries of science. But and then you get to and so you go through the data, you made it to the launch vehicle, and again, you monitor. In many cases, you're monitoring this right up and liftoff. In some cases, in smaller, lower cost satellites, you put it on the launch pad, put it on the launch vehicle, it's put on maybe with a number of other payloads, and you don't talk to it again until it's released from the launch vehicle on orbit. Um, the technology has matured to the point that if you tested it, before you made it to the launch vehicle and put it on, you got a high probability that nothing is going to change on the launch vehicle. But the more expensive the satellite, the bigger the investment, the more confidence you want at the moment you lift off. You've done everything you can to ensure it's ready for launch, so you monitor at the end. So there's some trade-offs between size and cost of the satellite and what you do in the processing. And then, of course, the next big thing is deploying it. It has to separate from the launch vehicle, and they're not always successful. Um, the second thing is once it separates, it has to basically get stable, be able to power positive, and that it's generating more power through solar arrays on board than it's consuming so that it can survive. It's warm enough and it can talk to the ground. And those are the early deployment tasks to make sure that through that process that you've got it on orbit stable and it can communicate with the ground and it can go around and survive and it's safe. And then the next stage, of course, is to calibrate the onboard instruments and make sure they're performing and their characteristics are understood on the ground so they can interpret the data from unknown sources. So you calibrate it with known sources and known devices and compare it to ground test data and take out any errors the system may have because of differences in temperature or shifts that might have occurred, alignment on the optics on launch. Once that's done, then you can start proceeding and looking at things you didn't look at before, new stars, new objects, and be able to interpret that data accurately. And so that's kind of a walkthrough of a space mission. And on that becomes how do I now optimize the collection of data, getting it to the ground, processing it, getting it to the user, making it useful. And I initially have a concept, and over time I learn how everything behaves, optimize that, and then I look for making that as efficient, as cost effective as possible, and getting maximizing the return on of science or data or communications throughput, whatever the mission is that the satellite is designed to perform.
Listening to that, it actually gives you a perspective on how much work actually goes into a mission, because these are the things people have no idea about at all. And just listening to the different stages that go into it, even probably days before launch, months maybe, I mean, it is a massive toss that you guys did. What was your favorite mission or favorite missions that you were a part of in your career?
Well, I mentioned that I first mission I worked on was the Orbiting Astronomical Observatory, and that was the kind of the first three-axis, fine-pointing, stabilized optical telescope put into space, um, and uh, that led me. We led us to look at, what is the next generation? How do we put up a bigger mirror? The power in a telescope is one of the keys to power is the light collecting capability, and that's generally directly proportional to the size of the mirror, and of course the quality of the mirror determines the resolution, but the ability to distinguish objects, because the smoother the mirror is, the less optical disturbance, and the finer point the object you're looking at, the finer resolution you can get, or bring it to a point, pinpoint observation. So we looked at things evolving the OAO from a 38-inch size mirror up to a 3 meter mirror. At that point, we were looking at, which was from a 1 meter to a 3 meter over time, and of course that gets to be big. Um, and we looked at what's the most effective way. One of the things that are important measurement point for the performance of a telescope, besides how big how what kind of light it can collect, is uptime. How long can I operate a ground-based telescope, for example? Doesn't operate in the days, right? So it's limited to the nighttime. Typically 8 or 9 hours of observing time is probably the maximum you can get from any observatory that's near the equator, and you want to be near the equator because polar observations are far less interesting. There's a lot less stars at the Earth poles. The Milky Way is more in line with the equator, and so that's why the Chilean Atacama Field is one of the premier observing spots in the world because of its location, high altitude, less disturbance, atmosphere to disturb it, less humidity, which is another disturbance of optics. So uptime is important, and when you get it on orbit, okay, the uptime is governed by number one, the reliability. Is it going to work perfectly? The second is how efficiently you can observe and take into account occultation of the satellite. The typical low Earth orbiting satellite goes around the Earth every 90 minutes, of which about 60 minutes are in sunlight, 65, 64 minutes, and about 30 minutes in darkness. And so if that was all you could observe, 30 minutes out of it, that's very inefficient. Okay. So what you do is look for and put on sun shields. If you look at um, JWST, it has a very huge sun shield the size of a football field, to give you an idea what huge it is, which is uh, in metrics, 300 feet by I think 60 feet wide, if I remember the number correctly. But the point is, it's huge, and you're blocking the sunlight, and allows you to observe. You're also blocking heat. In the case of JWST, it's in the infrared, so you want to reduce the heat to zero, and so that you can now pick something that's slightly above absolute zero out of the background, and that might be a planet around the star. So, but the point I was really trying to point out is how efficiently the telescope observes and how much uptime it is. So one of the things in the analysis showed is there were things in Hubble that you could get 30 to 40% efficiency. And ultimately, post launch, as I said, you optimized it. They got it up to 60% efficiency. That is, it could be on a target collecting photons 60% of the time. Now they looked at, okay, in addition to getting 30 to 40%, which was the design versus the actual, which the operations people were able to improve, they need to look at how do I make it reliable so I can make this super redundant. It's a very expensive. I can have every system. In the early days of the space program, we didn't know a lot. You made everything where you could 4 times redundant, especially in human spaceflight, where it almost took 3 full failures or 4 full failures before you were completely out of a capability. Some of it was two devices that were identical. Other ways were two different ways to perform the same function. So with Hubble in the late 60s, we looked at ideas for servicing it on orbit. And the space shuttle was in the study board, still on the boards for study and early development. One of the design reference missions was to be able to launch Hubble because that was the only thing big enough that would be able to get it on orbit at that time. And the second part was be able to use the shuttle to service it. So that became fun. And that to me, fast forward 20 some years later, I first when I joined NASA was to develop the operations for Hubble, but more importantly, I had the opportunity to lead the first servicing mission and lead it as a, a I was handed the program in effect, had turned over the program to me right after the finding of the that the mirror had a flaw in it, spherical aberration. But the flaw, we didn't quite know what the root cause of that problem was. And remember, earlier I said getting to a root cause of a problem is critical to know how to fix it or know what you knew about it. Um, and so I and at that point, Hubble nobody wanted to work on it. People that were so proud, including me, that worked on it at the beginning, I didn't do it, but others took off their bumper stickers, patches on their window, and um, didn't look their neighbor straight in the face because everything called it a major embarrassment for NASA, for engineering. Techno Turkey was a term used by one of our senators, Senator Mikulski, who later became a fan again. She was a great supporter of it. Then it embarrassed her, and then and so the on-air comedians they were always the butt of, Hubble was the butt of jokes, and that's when I inherited the program. It was a couple of and so we immediately, the first thing we had to do is kind of understand what the problem was. The second, we had to have a vision that we're going to fix it. The third, we had to give Congress, not the rest of NASA, the community, the scientific community, what I call the stakeholders, give them confidence that we had a plan and we're not going to repeat what we had last time. So that, and then I had to recruit people. I mean, who how to convince them that this was going to be a great project to work on. Fortunately, there was a core team, the people who I had worked with when I was at Grumman, who were still in NASA when I was at Grumman, and now they're still at NASA, who developed the servicing concepts and the ability to service Hubble on orbit, ensured that its design built in at least a large fraction of the capabilities needed to service it on orbit were part of the team, and they really performed the core technical um, team that actually pulled off the repair mission. My job was to number one to build a constituency, to support it, make sure the processes were there to adequately test it and develop it, and it was in I was the director and oversight guidance mode. I couldn't get into the technical details. If I did, we probably wouldn't have fixed it. So that was a good thing. But the point is, I had a great team under me. I also was responsible at that time for finding out what it can do and also building the next generation instruments, not only the repair for the first repair mission, but the follow on missions which were in the pipeline because Hubble was once launched to maintain that uptime. Decision was made that every 3 years it would have a servicing mission. Didn't know how fortunate that was to have a design to do that was able to overcome the initial flaw of the improperly ground mirror, but it also turned out over time, it's still operating over the next 5 servicing missions, we were able to not only fix it, but increase the um, data collection capability, put in new technology, higher resolution instruments, and we were getting 1,000 times the data return that we did from the initial deployment. in terms of data collection, data to the ground, and scientific information just due to servicing. So you want to talk about a mission that was very exciting. It also set the stage for the rest of my career. I mean, it positioned me and made me visible as a manager. I was selected to head up the Goddard Space Flight Center and ultimately to set up the human spaceflight program. So um, it was not only a thrilling mission, but it also played a major turning point in my career.
You mentioned Hubble and you also mentioned James Webb, but not that many people understand how important these telescopes are. So what are these telescopes? What do they do? And why is it that they are so important?
Okay, if I remember earlier I mentioned that NASA had I didn't mention, but kind of why we do space exploration, and in this case, robotically or using robotic spacecraft is there are kind of three scientific questions. Where did we come from? How did we get here? And are we alone? And kind of those are and so if you look at the fundamentals of space science looking out, um, it's the question of how did we get here? Are we alone? What's the universe? Is it expanding? At what rate? Hubble determined what's called one of the first measurements and was designed to do. Number one, it's an optical telescope at heart. It's designed to be in the visible, uh, ultraviolet, but the visible wavelengths. It does have some infrared capability to allow it to look at um, detect heat from objects in space, but not at the higher resolution needed to fully characterize planets and atmospheres around planets among distant stars that could be thousands of light years away, millions of light years away, maybe even one day billions of light years away. So, so Hubble is optical. It has a spectrometer, which basically a spectrum, and several different ones that look at what chemicals are being generated, what molecules are being generated by stars, and that tells you a little about the age and the makeup of the stars and the age. The second thing it can tell you is imaging, and imaging can um, tell you about uh, geometry between stars, galaxies, different gas formations around galaxies. And I'm sure you've seen the images of star formations with gases around. So Hubble could do that very well. Okay, JWST can do that, but that's not its primary mission. I'll relate the two in a moment. So the first thing I mentioned is Hubble was looking for what the Hubble constant is, and the Hubble constant was the fact that we knew the universe was expanding, but we didn't quite know the rate of expansion, and we also didn't know the size of the universe. And there are Cepheid variables. These are stars out there that have a known brightness and a known pulse of known variation in brightness. And so Hubble was designed as one of its primary is to measure these standard candles, they were called, and work backwards and use that to calculate how far away they were and how they were moving. And the way you calculate how they were moving is you look at the shift in the red and in the red wavelength. And what that means is the cyclic waves are further apart because the star is moving away from you. It's no different than what's called a Doppler effect when a train is coming and you're standing in the station, and when it's far away, it's lower pitched. As it gets closer, it gets high pitched. As it goes by you, it gets lower pitched. And pitch changes. So I'm not sure whether it's higher or lower. I have to think about it. Anyway, the point is, but the pitch changes based on the velocity of the train relative to you. Well, that technique is you look at the shift in light wavelength and you determine the speed by which it's moving. And so that tells you the speed, and the variable in light versus what you expected it to be tells you the distance. And so they developed it, and that's when they determined, and I think the current number is a little over $13 billion, $13 billion light years of age of the observable universe. And I use the word observable because we only know what we can see. We can postulate what might be beyond that, but we only know what we can see. So Hubble was designed to do that. JWST is designed to better refine that, which is interesting, but more importantly, to get better resolution. As you know, a number of missions over the past 10 years or so have been detecting exoplanets or planets that are sort of around stars that are in what's called the habitable zone, where the temperature is expected and the age is expected to be able to support life similar to what we support on Earth. Doesn't say there aren't other life forms and other evolutions of life that learn to evolve in different environments. But the point is, so right now, so one of the major goals of Webb is to be able to look at these planets at a whole nother level of detail and also look at ones in star systems that are further away and solar systems that are further away than Hubble at finer resolution and be able to actually look at a planet. And because I said it was in the infrared, so it's looking at for be, maybe 1 degree Kelvin warmer than the background. And being able to detect that and then start to be able to break apart what they see in his atmosphere in terms of temperature variations and chemical makeup. And then they get more finer understanding of the ability of that particular planet to form life, and then also learn a little about the evolution of it over time. And again, we're looking back to find out what's going to happen to us in the future. We got a lot of predictions. At some point, the sun is going to get so large and gaseous that's going to overtake the Earth. Is going to heat up, but there may be other effects. And so, being able to analyze these planets start to give you an indication of where there may be life at a higher level of resolution than we can get today. And number two, what happens to planets over time as their mother stars age and change.
A couple of the billionaires today, being Elon Musk, Jeff Bezos, Richard Branson, started companies that are focused in space tech. And you could say there's somewhat of a space race between these guys. But what I wanted to ask you is, what are your thoughts on the privatization of space activities, as well as your thoughts on NASA collaborating with private companies for missions, going forward as well?
Well, yes, there's a space race, but it's a different kind of space race. At least in my perspective, as a space race. There's a different kind of space. It's not the race between two countries or three countries to show dominance to the world and uh, beat our chest with pride over what our military might or our space might or technical might. It's a space race, much like any two companies in going to business making automobiles. They're each trying to develop a product, a capability that will sell, that differentiates itself from the competitor, that's maybe more affordable, maybe more luxurious, whatever the characteristics are. And that's healthy because it number one, in terms of space exploration, in terms of human space flight, and if I look at that side of it, um, but this does expand also to Earth resource measurements from space and non-human. But let me focus first on the human spaceflight side, and particularly um, if I look at Elon Musk and Jeff Bezos and Boeing and Sierra Nevada as one group of companies that are all proposing commercial or doing commercial delivery of people, commercial space, commercial human space flight. I'm sorry. Um, Clearly, they're competing with each other for a market to return on their investment and develop a product that's commercial. And that's wonderful because if it only took government funds, number one, the government has to be a lot more conservative. It's using taxpayers' money. Its processes, its oversight by the Congress is much more, and it becomes a political football during elections and changes in policy. And so it's a much lengthier, much more costly development process for advances in human spaceflight. If we look at the current Artemis program, it's been around for 20 years. In that time, SpaceX started from zero, became a company, developed a very reliable launch vehicle, and fundamentally has had, last year it had 60 to 70 launches. This year its goal is 100 launches. In the next couple of years, it's going to have alone had more launches than all the other companies in the world together. So my point that's great. It's developed with private money. Yes, it has a government customer. Yes, the government um, subsidized it in effect by guaranteeing it would buy services from it. But that's no different than when the airline started. So I think the commercial space development of human spaceflight is very important for us to advance human spaceflight in a time frame that keeps everybody motivated and not working on something for years and years and years and it culminates 25 years later in a product that goes on orbit. I think these uh, Amazon, they it doesn't happen overnight. Amazon, Blue Origin, I'm sorry, and that are working on things a long time, but they're also achieving things in far shorter time frames, much more cost effective, and opening it up not to you and or I can speak for me anyway, but the average person, but opening it up to some very wealthy people opportunities to get in space and experience what space is like, and hopefully motivate them to continue to support the spaceflight program, both the government side of it and also startup companies invest in them that are developing more and more capabilities that historically have been developed by the government, and using new technology is coming in a lot cheaper, a lot faster, and with far more capability. And I think this is wonderful. When I was at NASA, I encouraged both investment of studies at that time. We didn't get it off the ground quite fully, but to look at ways that private companies could actually deliver cargo. We didn't weren't to humans yet, but cargo to space station. And SpaceX had not come on the scene until near the end of my day, and they were certainly one of the companies that were had that as a vision. But there were also others, some using technology from the Russians in the U.S. that were going to integrate that into a capability. They didn't quite get selected, but Orbital Sciences did, which is now part of Northrop Grumman, and both Orbital and SpaceX are routinely supplying cargo to the space station on a commercial basis. And what that means is NASA pays by the flight and pays for success and delivery, and not just pays them to develop capability that NASA can use when they want, because they're using this same capability to deliver some of the private research capability to space station, and now we're seeing astronauts who are up there fundamentally on a tourist astronauts, so to speak, which heretofore the Russians were the only ones who really did that. So I think commercial space in terms of human space flight is important to really push the football down the field, so to speak, but also open up a lot more opportunities. Space hotels I see as a very viable thing. They could have been done years ago. There are modules up there. A company called Bigelow took over some technology from NASA called Transhab, a large inflatable structure that's currently one attached to the space station that certainly could house people up there for a week, 2 weeks. I mean, it doesn't have all the amenities that you would like a hotel, and certainly no swimming pool and golf course. But point is, they could house people. The problem up until a few years ago was, how do I get the people up there? There was no feasible way. The space shuttle was not about to be used to bring tourists up there. Um, and now Elon Musk has, had demonstrated it can be done. Boeing is not too far behind. Sierra Nevada is not too far behind. That is not, something that Blue Origin has a near-term uh, mission to do, but does in the long term intend to do it. Flying people around the moon in a module like Space Hab, uh, which could hold 6 to 8 people, and for a 7 day mission around the moon and back is not out of the question. There's no technological limitations on it at this point. It's getting investment, getting the idea, the belief that there's going to be a return on an investment, that you're not just spending a huge amount to put in place all the capability and finding out that the price per seat it's 100 years before you're going to close the business case. You really need to reduce the cost and also get the people willing to pay for the price that sustains a business.
Swimming in space sounds like a wonderful idea, especially in a hotel in space as well. I mean, I want to know where I could sign up for that because it sounds like a great holiday.
Think about it not only on space, but think about it ultimately on the moon, where there are accommodations on the moon where not necessarily private citizens, but private companies who have mining and other um, ideas about the moon could actually house people on the moon, have them go out in a spacesuit and do whatever they need to do to start doing exploration with a shovel and a pick, and there are lots of things that are all possible. Again, the question is there a business case that will ultimately close? Because if it's not government money, then there needs to be a business case that attracts investors. And once you start flying very wealthy people, you might stimulate their interest in taking a little bit of a risk. Maybe the business case doesn't quite close, but it has promise if we discover what we think we're going to discover. So all of this is kind of a self-generating um, industry, so to speak, that you need to keep motivating people to want to invest. You got to show return, and if you get some early returns on investment, it'll get more investment because it's unlimited. What potentially you can do in space in terms of mining asteroids and things like that, and returning things to Earth that are high value.
I mean, I wanted to get your opinion on a space elevator. I mean, when you look at illustrations of how a space elevator would look like, I mean, it makes you wonder about the physics at play to make that work. Do you think a space elevator is a possibility? I mean, when you look at how long it also has to be to reach the moon for something like that, or maybe if it would reach the ISS or something like that. But it's an interesting concept to say the very least.
I you know I've been asked to look at that, believe it or not, by a couple of people in private industry from time to time who were being asked to invest in it. At their companies, they the people in their companies that were looking for research money from the industry, and um, I I have never believed that it's physically possible. Okay, everything I just, but I have not studied it analytically. Okay, I have not. And I don't have the right skill set to go do the analysis and go do all of at this point. And so I don't really want to comment on it. But my initial take on our early looks at it with some people with the right skill set is, um, although an interesting concept, it sort of collapses when you really try to look at it and look at how it's going to sustain itself up there and all the other potential environmental issues associated with it. But again, that's a very flip and high level answer, and I don't think it's fair and needs to really be looked at by somebody in a lot more detail, a lot more money, and a lot more prototypes and kind of proving some of the concepts out.
Yeah, no, the physics to make that work seem incredible to say the very least. I mean, it is a tall structure, and most of the illustrations show it reaching the moon. So, yeah, I also wondered how it would be able to sustain itself at that great length.
You have the same questions that I do, and I don't have any answers. And you're right. It takes somebody to look at the physics and take it down. Also, anything like this, you really have to. Although things look good on paper, once you start to try to execute them and actually do something, you find out that things you never thought of. And if you're in the sales mode, you don't want to think of them. You feel when I get the money, I'll solve that problem. So,
I saw an article that said about 30 years ago, NASA was looking at reusable rockets with a project called DCX. I think it was called DCX. So, looking at the success of SpaceX with their Falcon 9 and all their other rockets that are reusable, why is it that NASA didn't focus their resources on working on a sustainable rocket, or at least trying to make it work? Seeing how successful this one was.
DCX was a program by a company run out of a company called McDonnell Douglas. And it was a lot of company money along with some government money. Um, they developed it, they demonstrated. They didn't demonstrate it was going to be able to carry large payloads to space. They demonstrated the vertical takeoff and the ability to land. And they had just, phase one of the program, built the hardware, flew it. Unfortunately, there was an operator or operational problem, an operator or operational problem. My recollection, it was some mistakes made in the operations, and it got destroyed after one or two flights. And the will of the government or McDonnell Douglas to start climbing that mountain again and reinvesting the money and building another one because the payoff wasn't obvious to anybody at the time for that particular design. Okay, there were several other designs that were being developed at the time. I think one was the X-37. I don't remember exactly, one by Orbital Sciences, I think the other by Lockheed, but and both of those sort of were canceled because when they actually got to look at them and look into these, it's one of these things where, um, in order to meet the cost targets, they didn't weren't necessarily they were experimental, they were high risk, and at the time we had a NASA administrator who was risk averse, and generally rightfully so. I'm not saying that it's a negative thing. And he evaluated, along with myself and the team, evaluated that the risk of flying these things, unless we put a lot more money into them, was too high, and the programs were canceled. But they were some early starts. There was also some looks at reusable boosters for the space shuttle, the two solid rockets. There was some very high level studies done looking at replacing those with two liquid stages that had controllable motors. See, solid rockets, you light them till the fuel is gone. They just keep burning, keep putting out thrust. You can't turn them on and off. But liquid motors. Not as powerful, but unless you make them huge, and we do that, of course. But you can turn them on and off, restart them. Especially the shuttle engines were one of the things that first things the main engines used were one of the first that were totally restartable. So the point is, they were looking at having some solids and having them fly back to Earth. The problem was money. Hey, the shuttle's working, the expendable rockets. By the time we develop these, the shuttle may be outdated in terms of its own technology, and it was never enough funding to get started on it. Elon started out with the concept to begin with. Remember, if you have a clean sheet of paper and say, what do I want to achieve? You can start factoring in all of these, and you don't always build them in initially, but you build in what we call typically hooks that you can add this capability later or demonstrate it. Once I get phase one done, I can now build this on phase two. Um, and so he started out on that path. And also, you have to look at the engineering behind it. They did an amazing job. The other thing is when you're dealing with your own money, and Elon and start up a lot of his own money and private investment, and don't have to answer to the taxpayers, only a small group of investors who bought into the risk, you can take a lot more risks because failure, you predict it, you get your team, your stakeholders to expect it. You don't have to answer to a bunch of taxpayers who you're spending my money on trying to do something. I don't even care why we're going to space in the first time. So if you remember, Elon had multiple failures, not of his rockets. He had a few rocket failures, but not anything to speak of. That in terms of his success record, the percentage is very small, and the reliability. He designed reliability into it. The fact it used 9 engines and one or two can fail, you still get to orbit is a NASA doesn't work that way. The shuttle, if one of the main engines failed, you could get to orbit or an abort site. But if two or more failed, you only had 3 engines, so two failing doesn't quite work that way. So a lot less reliability is another one. Robustness. Uh, Elon's rocket's very robust, but he had a lot of failures learning how to land, and he overcame them. and people, oh look, he failed again. He didn't. He got his payload on orbit, and this was kind of a secondary thing he did. Very smart. He didn't have these dedicated, I'm going to practice landing. He had in the beginning, he used that as a byproduct. To a couple of demos, he used it as a byproduct of his mission, and so he got to make the primary mission done. This was a secondary objective. It didn't work. It didn't work. However, the newspapers and a lot of people made a big deal out of a lot of that, poked a lot of fun out of it. Not fun, but seriously criticized it. Oh, look at this! He failed again, and it's like getting up at bat and hitting a triple, and somebody looking at you failing because you didn't hit a home run. And basically, it was purely not what they wanted to invest in. They did look at a number of industry proposals that talked about reusable boosters. There was one I remember that basically was totally automated, and there was a lot of resistance from the astronaut corps in those days. They were made up primarily of pilots, military pilots, and the last thing they wanted to be able to do was sit in a vehicle and not be able to control it, take over in case they needed it. And so there was a tug of war going on in the early studies. So a lot of it just never generated enough interest nor enough credible designs to pursue with an affordable cost to pursue. And Elon, again, money, private investment, um, can invest in whatever it chooses.
And looking at the amount of innovation that has went into the space industry in the last 20 years, what are some of the most interesting space technologies going forward or space missions that you're looking forward to in the space industry?
That's a great question because the last 20 years has seen, in my opinion, a great state change in space flight. Number one, there's a lot more commercial investment. That's an important point because commercial investment is pushing the state of the art of applications. How do I make this thing return money for me? Some of it is to sell brand new technology to the government, but in terms of technology, it forced them to look at how do I get greater return for less, how do I get greater return for my investment of products that are saleable? And so one of the things they wanted to do was, reduce the cost of launches. Elon did that. That over the last 20 years, I mean, 25 years ago, it was 40 to $50,000 a pound to put something on orbit, and now it's in the neighborhood of 5,000, and in some cases a little bit less, some cases more. Um, that's a big deal because that enables you, again, when you talk about that price per pound, the cost of launch becomes a great driver. And so you need satellites that are, very, very capable, and very reliable because the cost of getting them up there, you can't replace them. So the cost of launch came down. The second thing is people get clever. They always, when they see it, they say, hey, if I can get the weight of the satellite and the size of them down smaller, um, and get them to do some of the things that the large satellites do, I have a good double benefit. I not only cost less to launch them, but they weigh one heck of a lot less. So I multiply that the reduction in cost by a significant amount. So things like CubeSats, which performed, some of the early ones did very simple things, but you put some of them up there now have been sent to Mars. Others have done space physics experiments that heretofore required much larger satellites. And so you're talking about a satellite now that's 10 centimeters on a side, um, uh, a kilogram or less, a couple of kilograms that are but really light, and suddenly doing things that required original satellites that were you know uh, 100 kilograms, 200 kilograms in the past. Um, that's one. So now that the sensor technology was the key to that. Getting sensors that had the resolution, had the ability to do things that previously required very large detectors, very large cameras. If I can get with smaller cameras the same or better resolution, um, and so technology, micromineralization, growing detectors um, that that had uh, megapixels and tens of megapixels that were inches, digital cameras on those same kind of sensors, getting them on orbit, having them be able to withstand radiation tolerance and designs. That whole technology field allowed you to get to microsats and CubeSats that could do things that, in some cases, better than was done previously with large satellites. So that was uh, the second thing was computing and data storage. The the memory in your cell phone is far in excess of all the memory that was on the Apollo satellites collectively added up. Okay, today that's in your cell phone. It's in a chip that it's a very small size. A centimeter or less on a side, or much less than a centimeter. But you measure. So um, that technology allowed a number of things. Number one, it allowed you to have more elaborate computing in these small satellites. It allowed you to replace things that were pieces of hardware that were physical and took up space with software and computers. Radios, for example, or software radios with a little transmitter versus a big radio that was all um, uh, integrated circuits and piece of hardware. So you detectors again take large, vast amounts of data, but you need to store that or get it to the ground. So the technology having increased capacity on board of memories, denser memories, radiation hardened, and you went to having terabytes of memory built into your onboard. You could store data for days and send it to the ground, and then data rates, the ability to send high speed data to the ground increased over the past 20 years tenfold from smaller and smaller devices. So that collectively together allowed you to collect a lot more data, um, get it to the ground, where previously you couldn't. What you could collect in a year of Earth remote sensing data, uh, you can get to the ground in days now, and versus having to collect it over a year. They also allowed and so optical communications, another thing that increased from the planetary, the data rate back. Again, previously you'd wait, the data would come back. Things would come back and you'd wait 10, 20, 30 minutes and you'd get the first data. And by the time you got the next video, sometimes hours to get it. Optical communication now has reduced that time significantly. So all of these together have increased the capacity to get information back from satellites, from space, much more rapidly, much more frequently, do it with smaller, lower cost device, and has led us now to the era of putting in place constellations that allow us to make observations more frequently of points on the Earth because I have more satellites collecting data, allowed us to put the collection of Starlinks and other orbiting communications constellations that allow me to get data back from remote places on the Earth almost instantly or in very short periods of time, where previously it required getting it up, storing it, dumping it down, or sending it very high powered equipment. And frankly, in the middle of a lot of remote parts of the world, and even in this country, and in United States, developed countries, there aren't these high powered devices to get data. Now I can do that with cell phones and lower powered devices that can relay data from these little constellations. The reason having these constellations where they are is it doesn't take near as much power when they're at 1,000 miles or above the Earth, or 500 or 1,000 kilometers above the Earth versus something that's at 22,000 miles. The power from a cell phone can't go up to 22,000, but it can go to low Earth orbiting satellites. And there are companies like Lynx and others that allow you. The Apple, recent Apple innovation in their new cell phones of emergency communications through getting a cell phone. All of those things are a direct result of the technology that's been developed over the last 20 years. And I think we've seen advances in this that in the last 20 years that much more rapid than the prior 40 or 50 years.